Hello, this is Professor Gina, and this is the final video in the series of conic sections. This last section is looking at hyperbolas, and I've copied the picture that's in your textbook that has all the pertinent formulas and variables. You'll notice that the equation looks similar to that of an ellipse in the sense that it is in fraction form with a 1 on the right-hand side of the equation. A couple of differences are that there's a minus sign between the fractions rather than a plus sign. And with the ellipse, whichever number is larger is the one that we denote as A, and that will correspond with the elongated direction of the ellipse. With the hyperbola, in contrast, A is always going to be put underneath whichever variable is first, and that tells us, whichever one comes first tells us which direction the hyperbola opens. So in this first set of examples, A squared is underneath the x variable, so the hyperbola is opening in the direction of x, or left, right. And then in the second example, A squared is under the y variable, so we have the hyperbola opening in the direction of y, up and down. One of the other differences is that we have this Pythagorean identity, which for the ellipse was c squared equals a squared minus b squared. But here it's the traditional Pythagorean identity that you're used to seeing. So I'm going to spend a little bit of time explaining where the Pythagorean identity is in this particular example, or for all hyperbolas. So let's switch screens for a second to this is a GeoGebra, and it shows you how a hyperbola is created. Notice that we have two focus points, which are sitting in the interior of the hyperbola. And we have, if you think about a piece of string that attached to the two of them, and as I extend, this green line, which has the two tick marks, and this red line have a relationship with one another. The relationship is that no matter where we are on the hyperbola, the difference between them is the same. So if I took the length of the red and subtracted it from the green, that should be the same number no matter where I am. So what I'm going to do is show you what that common difference is, and it's going to be, I'm going to draw a separate picture just like I've got it here when both of those segments are lying on the transverse axis, or the axis that goes between the two vertices and the two focus points. So let's draw two hyperbola like this, like this, and then so our vertex point is here, and then let's put our focus point here. And we were wanting to see what the difference between this length is. One of the segments is going to be here, and then the other segment is going to be right here. So the center of this hyperbola is here between the two. Remember that this distance here is A, and then this distance is C. So if I think about the length of the green, it's going to be C plus A, because I also have A sitting right here, right, from the center to the vertex point. So that green is C plus A. And then the pink is, well, if I look down here, this distance is C, and this distance is A. So this little piece here, same as this pink one here, is going to be C minus A. And I'm trying to find the difference between these two. I'm saying that that's the common difference. It's going to be the same for any point on the hyperbola. Well, simplifying this, I get C plus A minus C plus A. I end up getting 2A. 2A is the common difference between any of the points on the hyperbola, no matter where we are. Going back to GeoGebra for a second. So if I move the point here and I were to measure the length of the green, subtract off the length of the red, that difference would be 2A, no matter where I am. And even if I change how the hyperbola looks, this lets me change how skinny or fat it is, the difference between these two is going to be 2 times A. All right. Now, going back to our examples here. The other thing that we need to talk about is this Pythagorean identity, c squared plus a equals a squared plus b squared. So I have this second picture over here on the right. What they've done is taken a hyperbola. The two vertices are here. The focus points are at 2 and -2, right? So this distance here is a. And then the distance from the center, or the origin in this case, out to one of the focus points, that is the length c. Now you can see this green circle that's drawn, and so that means that the radius going all the way around is a length of c. So if I look at that point here, that's c. So the, the axis that goes between the vertices is where A is measured, B is measured in the other direction. So this right here is B. Looking at a different triangle, same idea, but just the one down here, I have A squared and B squared being equal to C squared. So you can see that Pythagorean identity showing up in this context. The rectangle that we have drawn, it's not part of the graph of the hyperbola, but we draw it just to sort of give us a guide to draw the asymptotes. So we've got these lines that are showing up here, one that's got a positive slope, one that's got a negative slope, and that lets us know where the hyperbola is approaching. It's getting close to the asymptote, but not crossing it. All right, so let's do some example problems. Let's start with a simple one. Let's start with x squared over 1 minus y squared over 9 is equal to 1. Now, similar to the other conic sections that we've done, if we have the center not being at the origin, we will have a number being subtracted from x and from y. And in this case, we don't have anything. So we're going to say that the center of this hyperbola is going to be at 0, 0. Now, a is always going to be the first variable that's included, and because it's under x, that means that the hyperbola is going to open to the left and to the right. In this case, a is going to be 1 and b is going to be 3. We're taking the square root of both of those numbers. And then we'll use the Pythagorean identity to find the length of c, and that'll tell us how far the focus points are out from the center. So c squared is going to be 1 plus 9. C will be the square root of 10. And I get a decimal approximation so that I can use that for graphing purposes, about 3.2. Okay. So the center of our graph is at 0, 0. We said that the graph is going to open in the direction of x, and we're going to go out 1 unit from the origin to find the 2 vertices. So one will be here, one will be here. So our vertices are going to be at 1, 0 and -1, 0. The focus points are going to be beyond that the focus points are going to be at square root 10, comma 0, and negative square root 10, comma 0. So we'll draw those. Those are going to be at about 3.2. So about here. And then about here. Okay. And then B, and again, we're using B just to draw a rectangle so we can get the asymptotes. B is 3, so we're going to go up to here and to here so that we can draw this rectangle, which will be used to guide the asymptotes. Right, so the asymptotes are going to be like this. And then our graph is going to go from the vertex and then approach both of the asymptotes like this, right? Now let's figure out what the equations of our asymptotes are. As a reminder, we have this formula to find the equation of a line. We need a point and we need a slope. So we can use this formula, y minus y1 equals mx minus x1. X and y are the variables, and then x sub 1 and y sub 1 are a specific point. Now, we need to figure out the slope of the line first. And in this particular case, the slope is going to be, we're going to go over A, and we're going to go up B. So rise over run would be B over A. That'll give us the positive. And then we also have one that has a negative slope. So that would be negative B over A. So for one of our examples, I'm just going to use the origin as the point, because in this case we have the origin. We can use the center as the point that the asymptotes are going through. So y minus 0 equals 3 over 1 x minus 0. And then the other one is y minus 0 is equal to negative 3 over 1 x minus 0. So we have y equals 3x or y equals negative 3x. So these are my two asymptotes. These are the asymptotes. These are the foci and the vertices. And looking at this graph, I can see that it looks like those two equations, 3x and negative 3x, make sense. I'm going to go to Desmos for just a second, because most of you will probably look at the graphs in Desmos. And if you do, what'll happen is it's just going to look like this. Just the red part is going to be given to you. The asymptotes are not given. I graphed them here so you can see what they look like. And the foci are also not given. So I've graphed them so you can see what this looks like. So again, if you go to Desmos, it's just going to give you the red part of the graph, not the blue and not the purple. All right. Let's go back and do another example, one that's a little bit more complicated, with the center not being at the origin. All right, let's consider x minus 5, the quantity squared, over 16, minus y plus 2, the quantity squared, over 9 equals 1. All right, to start, we'll say that the center of this graph is at 5, negative 2. Remember that we're always subtracting off those two values, h and k, to get to the center. A in this case is going to be under the first variable. A is going to be 4 because it's a squared, and then b squared is 9, so b is going to equal 3. So c is going to be the square root of a squared plus b squared. C is the square root of 16 plus 9. C is equal to 5, right? Okay. So we know that this is going to be opening in the direction of x because x is the first variable. Let's start by putting our center. The center is at 5, -2. So here. The two vertices are going to be 4 to the right and 4 to the left of the center. So our vertices are going to be, well, we're going to go 5 plus 4, -2, and also 5 minus 4, -2, right? Going to the right and to the left. So 9, -2, and 1, -2. Darn it. So here and here. Okay, so those are our vertices. The focus points are going to be 5 from the center. So 5 plus 5, -2, and 5 minus 5, -2. So that'll be 10, -2, and 0, -2. Make those orange. One's here, one's here. B was 3, so we're going to go up 3 from the center, and then down 3. Need to make another tick mark here. And then I can draw this rectangle to kind of grab the asymptotes. So our asymptotes are going to be like this. And like this. Oops, that is not right. I didn't go down far enough, did I? 1, 2. This needs to be down more. Let me move this down. Counting is hard. There we go. It looked weird. I know my drawing's not the best, but that definitely was off. Okay, that's better. There we go. And then our hyperbola is going to be like this and like this. All right. Let's find the equations of the asymptotes. Again, we can use the graph that we've drawn to look at the slope, but there also is given to you just this formula that might be easy to use to find the equations of the asymptotes. The equation of the asymptotes is y minus k equals plus or minus b over a x minus h. Plus or minus because we've got one with a positive slope, one with a negative slope. So h was 5. Remember, h comes from the center and k comes from the center as well. This is h and this is k. So we'll have y minus a negative 2 and x minus 5. B was 3 and A was 4. All right, so I've got y plus 2 equals 3/4 x minus 15 over 4, or y plus 2 equals negative 3/4 x plus 15 over 4. 2 is the same as 8 over 4, right? So I'm going to subtract that from both sides. So I'm getting y equals 3/4 x minus 23 over 4, and y equals negative 3/4 x plus 7 over 4. Okay, I want to do one more example that has the hyperbola opening in the other direction, in the direction of y, and then also is sort of the most difficult problem you would see, where you've got the equation in standard form. So for this example, we'll have 9y squared minus 4x squared minus 18y plus 24x minus 63 equals 0. I'm just going to make a little note here on the side for standard form. Standard form of conic sections. If the numbers in front of, let's just call it like ax squared plus bx squared, and you've got some other stuff, right? If a is equal to b, if the numbers, sorry, this should be a y. If the numbers in front of the coefficients in front of x squared and y squared are the same, then that means we have a circle. If either x squared or y squared is not there, then we have a parabola. Let's put a little star, like this is one thing, this is a second thing. If there's a plus between them, right? If both are positive, then that means we have an ellipse. And if one of them is negative, then that means we have a hyperbola. Right? So that's kind of just some notes there on the side. In this case, we have one of them being negative, the second one, so we know that it's a hyperbola. The way that we approach this problem is by grouping the y terms together, 9y squared minus 18y, and then grouping the x terms together, and then moving the number, in this case, the 63, over to the other side. Now, I'm going to complete the square twice, once for the y's and once for the x's. But before I do that, I have to factor out any coefficient that is in front of the squared term. So before I get started, I'm going to take the 9 out here. I factor it out of both terms. And I'll take the 4, the negative 4, out here. Okay. And then to complete the square, I look at the middle term. In the first example, it's a minus 2. You take half of that, which is -1, and you square that. So I'm going to add 1 here. Now, really, I've added a total of 9. So I've got to balance that out by adding a 9 on the right-hand side as well. For the second set, for the x's, I look at the middle term, which is -6x. Half of that would be -3. Squaring that is +9. Really what I've done is I've subtracted 36, so I'm going to subtract 36 from this side to keep the whole thing balanced. Now I will simplify this. I have 9 times the quantity y minus 1 squared minus 4 x minus 3 squared equals, calculator, 36. Then we divide everything by 36 so that we get a 1 on the right-hand side. Y minus 1 squared over 4 minus x minus 3 squared over 9 equals 1. All right, so we're ready to start now. The center is at, so here's where you need to proceed with caution. Notice that x and y are switched. So in this case, h is here and k is here. So the center is 3, 1. A is going to always be the first variable, so a will be 2 and b will be 3. C is going to be the square root of a squared plus b squared, which is the square root of 13. Which is approximately 3.6. Okay, I think we're ready to get a graph going here. So our center is at 3, 1. This is going to open in the direction of y. So the vertices are going to be 3 up and 3 down, no, 2 up and 2 down from that. So our vertices are going to be at, so we're going to go up from the center. So 3, 1 plus 2. And down, 3, 1 minus 2. So 3, 3, and 3, -1. Center is here. All right. And then the foci are going to be up and down from the center as well. So 3, 1 plus root 13. And 3, 1 minus root 13. I'll put a little mark approximately where those are. So let's see, our vertices are going to be 3, 3. So here, and then -1 here. And the foci are about 3.6 up. So let's see, 1, 2, 3. So about here, 1, 2, 3, and about here. Okay. And then B, the length of that was 3. So I'm going to go out 3 to the left and right. So I'll go here and here, and then I can draw my rectangle going there along the y-axis. And then I've got my asymptotes. And then my graph is going to open up and then also down. All right, last part is to find the equations of the asymptotes. So y minus k, in this case, we're going to do a over b, right? Because we're opening up, this going up is a, and going this direction is b. So the slope is going to change. We're doing rise over run, so a is the rise in this case. And then x minus h. So y minus k was 3. No. 1. A is 2, B is 3, and then x minus 3. So y minus 1 equals 2/3 x minus 3, no, minus 2, or y minus 1 equals negative 2/3 x plus 2. And we'll add 1 to both sides. Y equals 2/3 x minus 1. Y equals negative 2/3 x plus 3. So those are your two asymptotes. Okay, thank you for watching. If you have questions, you can send me an email. Have a great evening.